Yes, welcome everyone to geohug. So before we kick off today's session, I'd just like to take this time to acknowledge the traditional lands which we're all coming from today. I'm here on the beautiful lands of the Gadigal of the people of the Aurora Nation, and I'd like to pay my respect to the elders past, present and future. So I'm thrilled to have Ayesha Ahmed with us today. So Ayesha is an applied geochemist, geologist with over 15 years experience in academia and industry. So her current role is senior geochemist with Teck Resources based out of Vancouver. She's passionate about integrating innovative analytical techniques with fundamental geoscience concepts to maximize value from data, leading to improved rock characterization for targeting, modeling and mining. And it is going to be amazing to hear her insights today on transformational orebody knowledge workflows, the data behind the vision. So it is going to be an awesome session. And yes, thanks so much, Ayesha, for joining. It's amazing having you.
Thank you so much. Thanks so much also, Jessica, for the invitation, and to Teck Resources for giving me the opportunity to speak, and to Cam for really kind of lightening the mood. I'm always a little nervous before a talk, and this really helped to get rid of those nerves. And I'd also just like to do a land acknowledgement here. I'm sitting in my house in Vancouver in Canada, and I'd just like to acknowledge that it's situated on the unceded traditional territories of the Musqueam, the Squamish, and the Tsleil-Waututh nations. So today's talk is really the result of a number of core scanning trials that have been run at Teck over the past few years. And some of these have been successful trials, and some of them not so successful. And in the end, what this success really boils down to, after all of the state-of-the-art technology is done and dusted, you know, the thing that separates something successful and failed is the quality of the data that we've produced. So, you know, we can all know the opportunities that rapid high-resolution quantitative data presents, and I'll talk about some of these, for transforming geoscience workflows. But I think understanding and quantifying the limitations of that data is absolutely critical. So that's what I'll be talking about: practical steps and ideas to ensuring that we have the workflows in place to measure performance of new tools, technologies, and specifically core scanning XRF. Before I go any further, I just almost forgot, want to acknowledge my co-authors, Paul Carney and Kevin Byrne from Teck. Okay, so let's start big picture. I'd like to frame the problem or the challenge here with a quote from someone named Andrew Ng. He's the co-founder of a company called Coursera. They offer online data science courses and actually a load of other courses. So strongly encourage you to just go online and check them out. But what he says is the model and the code for many applications are basically a solved problem. Now that the models have advanced to a certain point, we have got to make the data work as well. The way I interpret this quote is that machine learning continues to be a hot topic in geoscience. And as we collect more and more data, we're thinking about how we can use machine learning and algorithms to extract the most out of that data. But basically, you know, the algorithms haven't changed a whole lot over the past couple decades, or at least the ones that we routinely use in geoscience, working with geoscience data. So, you know, random forests, clustering, principal components analysis. These are all, you know, 10, 20, 30 years old. The new data streams that we're feeding into these algorithms, they are really the next challenge. So let's look at one of these data streams. If you've been to any conference recently, you've probably seen a dozen or more service providers presenting their kit. So there are dozens of these service providers on the market right now, and they're all offering some combination of X-ray fluorescence for multi-element geochemistry, hyperspectral data collection for mineralogy, high-resolution RGB imagery, and some even magnetic susceptibility and Lidar. I am not here. I need to make this very clear, putting on my tech hat. I'm not here to sell you on one company or another. There are pros and cons and use cases for different scenarios. But I'll just kind of walk you through what this machine does. So you can see that on the left-hand side of the screen, there's an opening. That's where the core, if we're analyzing core, is typically fed in. It's placed onto a core table, which is a flat surface. And then there are kinds of two options. Either the table itself moves relative to a bunch of sensors that are located on the roof, or the sensors move relative to the core table. And different sensors are mounted on typically an XY track. So your XRF sensors, your cameras, and all that jazz. But, why do we collect this data? This is not cheap. It costs somewhere between, $20, $30 a meter, all in cost. So why do we want to collect this data? And how can we use it in exploration and ore body knowledge workflows? Well, I see a few different pathways to value, if you will, for these data sets. The first is the immediate value that we can get. And that's really, on a 24-hour turnaround kind of data stream, we can use this data to support drill core logging, using quantitative data to remove some of the subjectivity that is inherent to a person logging core. We can also get quantitative grade estimates, so we can stop relying on manual visual estimates of the kinds of grades that we have in our core. We can also use it to help to pick out areas of sampling, whether that's for geometallurgical sampling or just assaying. So we can use these quantitative data almost in real time to really support the geologist in the field. Then we have this kind of longer term value add. And that's really what we do with the data once we've had some time to sit down and ingest it and interpret it. And in that case, we're looking a lot more at de-risking the ore body. Because we're collecting data, and I'll get into this in a couple slides, both at the centimeter scale as well as the meter scale, we have the ability to move between different resolutions of data. So we can use data to investigate things like element deportment. We can look at material classification, generating proxies for hardness and recovery to understand how this material is going to perform further downstream in the mill and the plant. We can also create proxies for things like neutralization potential and acid potential. These are acid-base accounting parameters that we're never going to replace the original commercial laboratory data that we collect, but that data is typically very sparse. It's the same with geometallurgical data. We only have samples, a few hundred or maybe 1,000 samples for an entire deposit. And what collecting this core scanning data does is it allows us to really beef up some of those population statistics to get a better idea of the spatial distribution and variation of some really key parameters. And then lastly, we have what I've called kind of an unlocked potential. This is collecting these quantitative foundational data sets that answer the questions that we haven't even asked yet, that happen 5-10 years down the road when somebody asks, well, how do we model this variable? And when we collect these kinds of quantitative data sets, we have that data ready to go to answer those questions. When we, look across all those paths to value that I just described, for me, the common theme is around multi-element geochemical data. It's the most versatile data set to answer questions right through the mining value chain, from exploration through to production. Now, of course, every geological challenge or problem will have a different solution. So for you, maybe that will be shortwave infrared, or it's your RGB imagery. But for the rest of the presentation, I'm really going to focus on XRF because that's the data set that I've used most. So I'm just going to show you a really quick video here. There's no sound, but it's just going to show you what this actually looks like. So, if you kind of picture back to that core scanning trailer that you saw, and you remember there was that opening on the left-hand side where the core goes in, what you're going to see in this video is one of these sensors. This is the XRF sensor that's housed. I don't know if you can see my mouse, but it's housed in this area here, and it's going to be scanning over the core. And in the next slide, I'll show you what's happening within that sensor. So here you can just see that the sensor is maintaining about a 1 centimeter distance between the head of the sensor and the core. The sensor then gets to the end of the core tray and it lifts up, and then it moves to the next row. And so this is how it collects the data. This is just a dummy example. It would usually go much more slowly, typically takes 10, 15 minutes for a box of core, depending on the vendor. So what's happening in the background? What's happening in the head of that sensor to collect XRF data? Want to make it really clear here, and it's probably going to become evident by the way that I explain it, but I am not an XRF physicist, and I'm not going to do a deep dive into the physics of this method. I think it's actually quite complex when you look beneath the surface, but I wanted to get everyone on the same page with how the basics of XRF work, because some of the subsequent, this information is relevant to some of the subsequent slides. So X-ray fluorescence occurs when high energy radiation, which is emitted from an X-ray tube, it excites atoms in a sample material. So for us, that's core or rock. And it does this by displacing electrons from the innermost orbitals. So when the atom relaxes after having electrons kicked out, outer electrons fill these shells, and then X-ray fluorescence radiation is emitted. Now, the radiation that's emitted, it's kind of like a fingerprint, where different elements have characteristic peaks and characteristic energies. So very simply, we can use the energy of the peak and the intensity of the peak at a given energy to tell us about element concentration. Very crude explanation. Now, the best part about XRF is that it's pretty fast, and it's a way to get total element concentration. So it's not like an aqua regia digest, an ICP, or even a 4-acid digest, where we're leaving some material behind that is not dissolved. There's no digestion required. You can, but you don't need to. It's non-destructive, so the sample isn't damaged during analysis. The bad part about XRF, or the challenge perhaps, is really to do with the lighter elements like magnesium and sodium, where X-rays are emitted from the source, but they're attenuated in the air. So they lose their power before they actually hit the sample, and they can't excite elements in the lower energy range. So that's why with things like portable XRF, we don't get sodium. And then there's the ugly part of the XRF, which is just pretty much saying the bad part number 2, and that's matrix effects. This results from X-ray peak interferences, so where those characteristic fingerprints actually overlap with fingerprints from other elements. But even with these challenges, XRF remains pretty much the best, most rapid analysis multi-element geochemical tool on the market today. And we've seen that with the widespread adoption of portable XRF by the mining industry. What I show up there is in this amazing animation is just the air gap. And this is a concept that we're going to come back to in over the next few slides. But really all it is it's the distance between the XRF head, the sample, and the detector. And what happens is if this air gap is really big, the signal is attenuated, the X-ray signal is attenuated, and it doesn't reach the sample, and then it doesn't reach the detector. So with a portable XRF, for example, you might have seen that you actually need to have the XRF nose directly on the sample and ensure there's no air gap. Otherwise, you don't get a very good signal. And so really, when we think about it, we talked about the good and the bad. I think the idea really is that you just can't have it all. We have to be honest with ourselves. If we want to get and achieve benchtop XRF levels of precision and accuracy on both light and heavy elements, well, then we need to use a benchtop XRF, and we need to prepare our samples accordingly, using fusion or creating a pressed pellet out of pulverized material. And then we need to be prepared to wait that multi-month turnaround that we have to at a commercial laboratory. If we want rapid data turnaround and we're happy collecting data on spots, then portable XRF is your way to go. You lose out on sodium, but most other elements are pretty decent. If we want the rapid turnaround time, and we're willing to sacrifice some of the lighter elements and some detection limits, then and we are willing to acknowledge that drill core is unlikely to ever be perfectly smooth, so we will inevitably be dealing with some geometry issues with the XRF. If we go into this knowing that we have to make these sacrifices, then we can factor them in to the way that we interpret data. All right, so now we're going to get into kind of the QA/QC workflows of how we actually ensure that we're collecting good XRF data in the field using scanning XRF. But before doing that, we have to talk about what the benchmark is. And the benchmark is really the commercial laboratory XRF workflow. So XRF has been offered in commercial laboratories for over half a century. So sample preparation, the analytical methods, they're very well established. And I'm going to speak on behalf of industry here, but I'll say we have expectations from our commercial laboratory partners when we send them our samples. And one of those expectations is that they have a quality assurance and quality control program in place that uses certified reference materials, blanks, duplicates, maybe, umpire, round robin processes. And the point of that is to really monitor every part of the laboratory workflow, from preparation to analysis and reporting. Separate to that, industry, it's required from an NI 341 or a JORC perspective, we have our own QA/QC workflows. And those also include certified reference materials, blanks, and duplicates to ensure that the entire workflow from sample collection right through to preparation, analysis, reporting, that chain of custody is maintained. So anyone who's worked in industry, anybody who's worked at a lab, this is a no-brainer, right? It's absolutely nothing new. The question is, what is industry best practice for scanning XRF workflows? And the answer is there is no best practice. So I'm going to just cut to the chase there. This is an actual quote from one service provider that we worked with a couple of years ago. And this is not the only time I heard something like this, but it was, we don't need standards. We tested our XRF 12 months ago and it was very stable. And anybody who's worked in analytical geochemistry would be horrified by this statement, right? In a commercial laboratory, you are evaluating the stability of the XRF on a daily basis with every batch. So it's a really quite a different mentality when we start looking at scanning XRF and the expectations. So, from my experience, I don't want to complain anymore. Let's talk about a solution. So what can it look like? How can we actually collect robust data in the field? From my experience, the optimal approach to QA/QC in scanning workflows has three components. Some of these are already done by service providers in the industry, and some of it is new. So the first part here is what happens before you take one of these trailers into the field to your mine site or to your project. This is a pre-programmed component comprised of developing a matrix-specific calibration to turn XRF counts into concentration data. So what does this look like? It requires you to give the service provider pucks, so whether those are old assays or pulps, not coarse rejects, old pulps that you press into soil cups, and then you analyze those with XRF so that you've got your assay data and your XRF data. You can also scan a bunch of drill core that has associated assay data, and then you can develop this calibration that helps you to link the counts at each of the energy peaks to the different concentrations. This is really important because there is no such thing as a global XRF calibration, really. In this scanning XRF environment, where you are scanning in situ core that has not been processed, it's really important that the calibration that you develop is specific to your rocks on your project. Again, this is nothing new. All of this has been described for portable XRF best practice guides. And then next is the in-field component. And this is really, I think, where the gap is in the industry right now. I'm talking about routine analysis of QC materials, so standards, blanks, duplicates, analysis of core boxes at the beginning and the ends of shifts, processing the data daily and validating the data daily so that we can initiate rescanning or address issues as they come up on a daily basis, instead of waiting until the end of a program to realize that the 3 weeks of data you collected was total garbage. And then there's a post-program component. And this is really where XRF data are validated against assay data that was collected that season or over a period of time. And then that data can even be fed back into the calibration to improve it with more training data. So doing this kind of validation is it's really good after a scanning program is complete, but it's all very post-mortem, retrospective. And it provides really no indication of how the tool is performing on a day-to-day basis. So let's look at what we can do in the field on a daily basis. The first quality control measure that we can use in the scanning XRF environment is the duplicate. So given that this is core scanning, it's meant to be rapid analysis. The last thing we want to do is bog down our workflows with too much quality control, right? We still want this to be fit for purpose data where we're getting rapid turnaround. So we have to make compromises. What we did is we collected a duplicate that kind of targets 3 aspects of variability. Variability associated with manual handling, variability associated with the path of that the XRF takes over the core, and geological variability. So how homogeneous is the sample material? The way we collected this data is we collected an original scan of the core. And if you imagine the way that the XRF works is it's not scanning the entire width of the core. It's scanning like maybe a 9mm swath on the top of the core. So we get our original line scan. We then take the box physically out of the core trailer. We put it back in, and then we create our duplicate. So this type of duplicate will measure a few things. First, it measures the pretty minor variability associated with the manual handling. So by removing the core tray and putting it back, you're likely shaking up the core a little bit. The box is not going in exactly the same spot. So you're likely to be scanning a slightly different part of the rock. Surely some overlap, but a slightly different part. It also measures the reproducibility of where that XRF head is actually scanning on your core. The way that this pathway is developed is actually using LIDAR. So a LIDAR scan is done of the core. It creates a map of the core. It shows where there are ridges and where the curvature of the core is. And from there, it will create a path for the XRF to scan. So by having a duplicate, you can see, okay, is the LIDAR working in the same way? Am I getting the same path twice? And then finally, we're measuring geological variability as well. So in a very homogeneous rock, we would expect the original and the duplicate to be almost exactly the same. But in a more heterogeneous rock, where you might have your line on two slightly different parts of the core, and those two different parts are different, then you would expect to see some more variability. So similar to what we would normally do with duplicate pairs in conventional QA/QC workflows with commercial laboratory data, we can use conventional statistical methods. We can use regressions on the left, min-max hyperbolic graphs on the right, in order to assess quantitatively how much of our data is passing or failing. Do we have biases? If our data is failing, if it's plotting above that red line that you see, is there a geological reason why that's happening? Or do we need to go back and rescan? So just by collecting this data, we're giving ourselves the option to quantify how well the instrument is performing and make a decision based on that. So the next thing we do is analyze a number of certified reference materials with each box. So 3 certified reference materials with each box. And these were matrix matched. They're actually developed from the deposit that we were working on. So it's good material from that deposit. And initially we had wanted to make nice fused disks, because that would kind of replicate the density of the core the best. Unfortunately, when you're creating a fused disk, you have to dilute your sample, usually by a factor of about 10 when you add the flux. So it's very difficult to get the right dynamic range of all your elements of interest when you're diluting it. So our compromise was to create these pressed pucks. They were pressed to a pressure of about 3,500 PSI, which approached the density of our core. And so the idea here is that with each box, before the box is scanned, the XRF head passes over a number of these standards, and you're able to plot them exactly as you would normal standards on control charts to understand the precision and the accuracy of your data. We use the same XRF settings of the core. We had the same height every single time. However, as you would expect, it's a different programmed path to the drill core. So it's not a perfect solution. We're not perfectly able to mimic the settings of the XRF on the core, but it still gives us a really good idea of precision, accuracy, as well as drift over time when we start to monitor on a daily basis and perhaps even monthly or biannual basis. And really, what's integral to this process is this idea of daily data validation and daily uploading in order to really make real-time decisions. So we don't leave the field with bad data. We can action it in the field. Something that I'm really excited about, and this is something that we don't use so much in the commercial laboratory space, is how we can use LIDAR to validate our XRF results. So the idea with LIDAR is it maps the distance to an object, just measuring the time for the reflected light to return to a receiver. And if you remember from a few slides back, I described that it's the LIDAR that's used to actually define the pathway for the XRF head over the core. The idea is that at all times, if we're in the best situation possible, At all times, the XRF head maintains a constant distance from the core. So this air gap that we see here is constant. What that means is that if your core surface is uneven, so if you imagine this is kind of a side view of the core, you have a nice solid piece of core, then you have, a half slab of core, and then back to a nice solid piece. You really want that XRF head to follow along all those grooves and maintain a constant gap. If it were a perfect world, then all of our samples here, we can see this is from on the x-axis here down the hole. We're looking at our air gap. So this is the distance between our XRF head and our core all the way down the hole. In a perfect world, this would all be around 1 centimeter. But we can see that it isn't. We have quite a lot of data where the air gap is significantly greater than 1 centimeter. So what that's telling us is that we haven't been able to maintain that consistent air gap throughout the scanning process. Why do we care? Well, the problem is that when our air gap increases, our concentration, perceived concentration, decreases significantly. And so here you can see this is an air gap of 1 centimeter to 3.5 centimeters, and you can see a decrease in our calibrated alumina value of 7%. So how do you know when you're looking at a downhole graph, how do you know that the changes you're seeing in alumina are actually geologically controlled and not simply a function of the XRF head? When we look at heavier elements, they're less affected by signal attenuation in air. However, you can still see a smaller decrease in the concentration with air gap. But the fact that we're able to identify this, the fact that we can see where we have large air gaps, where we have reasonable air gaps, again, it gives us optionality. It gives us the chance to make a decision about whether we want to keep the data, whether we want to rescan it, or how we're going to use the data. And for me, that's probably the most important, is understanding the limitations of the data, not discarding it necessarily, but using it to inform the appropriate scale of observation. So for silica, for example, a light element strongly affected by this air gap, I might not look at centimeter or even meter changes in silica. I might use that in a drill hole to look on the 100-meter or 200-meter scale for major formational differences in silica. Okay, so now comes the fun part, right? So after validating our data using standards, using duplicates, Lidars, then we can be confident that the variability that we're seeing in our data is actually a function of geological processes and not simply variability in our data collection parameters or instrument performance. And then we can be confident in feeding this new data stream into the multivariate or machine learning workflows of our choice. So here, I'm showing XRF data that's been tessellated. We apply a principal components analysis. You do some clustering, and what you end up with is 3 beautiful layer cake stratigraphic units that plot really well spatially in space. And we need to do this step of validation because so many of the algorithms that we use, like principal components, like clustering, they rely on defining sources of variance in the data set. So if those sources of variance are not geological, those algorithms will still find you groups, but they're not going to be telling you what you want to see. We want to get the data right so that we can realize the initial value proposition of the core scanning, that immediate value of helping us to do geological logging, giving us, instead of just using our eyes, less subjective quantitative data sets to base decisions on. It also allows us to create those long-term value products, developing geochemical proxies for data sets that are really sparse, typically in the advanced projects workflow. And then, of course, again, just collecting good data to answer questions for the future. Something that I'm quite interested in now, dealing a lot with this data, is really on the data management side. Find it really, really interesting that a lot of the databases that we use to house this data are not ready for big data. We're currently having to downsample the data. We're not maximizing the optimal resolution of the data because our databases can't handle it. Uploading the data, takes 25 minutes, which isn't optimal when you're up in the middle of nowhere in the Arctic. So, really thinking about these core scanners and these workflows, not as just isolated pieces of data collection, but really how we integrate it into the exploration and resource extraction workflow, from data collection right through to validation, data management, and then making that data available to users. So finally, this is coming from my own experience working with service providers on this topic in specific. I think there's a gap that we're in the process of bridging right now. And I think it has to do with expectations from the industry side and the service partner side. So, as an industry, as clients, when I think about how we use this data and what my expectations are, it's that the data are precise, accurate, they're answering the questions that I'm asking, the data's deliver on time, and the data's secure. From a service partner focus, and again, I don't want to speak for every service provider out there, what I've seen so far is that there's just a lot of focus on hardware functionality, adding new kits, new sensors, maximizing the product efficiency and the scanning rates, right? So that you can scan 600-700 meters a day. And somewhere in the middle there is the optimal product, where we marry the rapid turnaround and we marry the product efficiency with data quality. So I'll leave it there. I'll summarize here by just saying that there are many examples out there, some of which have been presented on geohug or Deposits Hub, that really showcase what can be done with rapid analysis data sets, specifically core scanning data sets. The potential for transformation is clear, especially as we leverage these different technologies to collect routine data, because it's freeing up geoscientists to do the big thinking work that we all spent so many years, in school for. So my pledge, I suppose, is, as industry and in academia and with service providers, we need to be accountable for these data. We need to work closely together to ensure data quality and integrity. And the only way to do this is by going back to the basics and developing rigorous quality assurance and quality control programs, which will give users of this data across the mining value chain confidence to use them. So thanks very much, and definitely open to comments and constructive criticism and questions.
Thank you so much, Ayesha. That was awesome. I really, really appreciate you taking the time to talk to us.